All right, let's talk specifically about atomic masses. So we looked in the last video at how we figure out what atomic mass is, protons and neutrons, and what an isotope is. So the atomic masses that we see on the periodic table are actually based upon carbon-12. What they decided is the mass of one carbon-12 atom is exactly 12 AMUs, and everything else is based off of that. So for example, magnesium we say has an atomic mass of approximately 24, and the reason they decided it's 24 is because it weighs approximately double what carbon does. And so since they said carbon-12 is 12 AMUs, magnesium has to be 24 AMUs, and so on and so forth. So the mass that is given to you on the periodic table is actually an average of all the isotopes of that particular element. So when you look at carbon, we know there's carbon-12 and there's carbon-14, but on the periodic table it says 12.011, which isn't the average of 12 and 13. And that's because they also take into account the abundance of the particular isotope. So in actuality, carbon-12 is a lot more abundant than carbon-14. Therefore, when we calculate the average, we give more weight to the 12 than we do to the 14. If we just average them directly, the average mass would have been 13 on the periodic table. However, there's a lot more 12, and so it weighs heavily towards 12. And if you were to go outside and grab a chunk of carbon, what you're going to find is that the average mass of that thing right there is going to be about 12.011, and that's because in nature you're going to have a certain amount that's carbon-12, a certain amount that's carbon-14, and they average out abundance-wise to about the mass that's on the periodic table. So how do they figure out these atomic masses? It's not like you can take a single atom of carbon, set it on a scale, and write, okay, this is about 12 AMUs. Instead, they have to use what's called mass spectrometry. So this is actually pretty cool. What they do is they take a sample, a pure sample of an element, so carbon, magnesium, whatever it is they want to study, and they run it through an electric beam. And so you look right here, here's our sample, and they're going to shoot that sample through a beam of essentially electrons, and as those electrons pass through the sample, they're actually going to remove electrons from that sample. So if we were doing this with carbon, it would rip some of the electrons off of carbon, and what we'd wind up with then is a carbon with a positive charge, 2 plus, 3 plus, it doesn't really matter. And so as it goes through then, it's going to pass through this guy, and that speeds it up. So it essentially throws it between two plates, a positive and a negative plate. So if we've got carbon plus, that carbon plus is going to be repelled by the positive plate, attracted to the negative plate. And so as it goes through here, ding, it bounces it down, and then it hits a detector plate somewhere over here. Now, think about this. If we've got a really heavy element that goes through here, how much is it going to deflect? Think about a bus. A bus is driving past you and you give it a push. How much is that bus going to deflect from its original course? Not very much. Why? Because it's massive. Then think about a 2-year-old running past you and you give it a push. How far is that 2-year-old going to stray from its course? Pretty far. Why? Because it's lighter. And so scientists can then calculate the relative mass of an element based upon how far it is deflected from its original path. So the angle that's formed right here. Lighter elements will have a much steeper angle. Heavier elements will have a much shallower angle. And then based upon those angles, a little bit of physics, and some hand waving, they're able to calculate what the average atomic mass is of each individual isotope. And so if this was, for example, carbon right here, its paths, we would see one here and one there. And so this one that's deflected farther down, that would be the carbon-12, and this one up here would be the carbon-14. And so since scientists saw two different lines, they assumed, all right, carbon's got two different isotopes. Not only do they see the masses and where they're hitting, but they can also count the number of times each particular one hits. So a scientist who's observing this is going to notice that most of the carbon atoms are hitting down here with 12, because that's the larger abundance, but a certain amount, a smaller amount, would hit the 14. So here's an example of some data that a scientist might gather. They would do this with pure sample, the setup we just saw. They would see two different places that it was hitting on the detector plate. One would be about 107 AMUs, and the other one would be at 109. What the scientists noticed is that 51.84% of the collisions against the detector plate were from the 107, and then 48.16 were from the 109. That means the percent abundance, you're going to have 51% that's 107, 48% that's 109. So these numbers that are down here are kind of the rounded masses. What we're asked in the question then is we know that the mass for the 109, so this guy right here is actually 108.90476 AMUs, and it wants to know what the actual mass is for the 107 version. Alright, so what we're going to do then is use an equation that's actually a fairly common equation and one you're going to need to know. That equation is that the average atomic mass is equal to the abundance of a particular isotope times its mass plus the abundance times the mass. So the average atomic mass, this is what you see on the periodic table. So that big long fraction decimal that you see on the periodic table, that would be the number that goes right here or that you calculate to go on the periodic table. Abundance, this would be the percent that abundance of the particular element in fraction form. So for example, in this question, we're dealing with silver, which has an abundance of 51.84%. In fraction form, that would be 0.5184. And then mass, that would be the mass of that particular isotope. Okay, so for this particular question, we know the average atomic mass of silver. That's what's on the periodic table. We can get that from there. We know the percent abundance of isotope 109, and we know the mass of 109. It's 108.90476. We know the abundance of the 107, but we don't know the mass, so this is what we're looking for then. So the mass in my periodic table of silver is 107.87 AMUs. The percent abundance of the 109 is 48.16%, so in fraction form, 0.4816. We add that to our unknown mass of silver times its fraction of abundance. And then if we go ahead and rearrange and solve, we can see then that the mass, the AMUs of silver 107 is going to be 106.9 AMUs, and I'm assuming that you guys can do this kind of algebra on your own, solving for that guy. All right, here's one for you guys. Go ahead and pause the video, read this question, and give it a shot. If you're not sure how to do it, don't just resume the video. Go back, watch the last slide, the last practice problem, and try and do this one. Don't go on and finish this video and check the answer until you have something written down. All right, so for this question, we were given the percent abundances, we were given the mass of the two different isotopes that appeared, and asked to find the average atomic mass, so the number that would go on the periodic table and get printed there. And so just converting those percentages into fractions, multiplying them by their particular mass weights, we would find that the AMUs of this actual atom would be 35.45 AMUs. And you can conclude from that that this is probably chlorine we're looking at.